Let's take a closer look at what happens when a firefighter climbs a ladder. When a firefighter climbs a ladder, we expect and hope that the ladder will not move. If the bottom of the ladder rests on ice or wet concrete, the ladder might slide. In the example in the textbook, the firefighter stands 6.30 meters from the bottom of the ladder, with the distance measured along the length of the ladder. The free body diagram shows the forces acting on the ladder. W sub L is the weight of the ladder, and W sub F is the weight of the firefighter. G sub X and G sub Y are the horizontal and vertical components of the force exerted by the ground on the bottom of the ladder. And P is the force exerted by the wall on the ladder. We assume that the wall is smooth. This means that the wall cannot exert a frictional force. It can exert only a normal force. Therefore, P must be perpendicular to the wall. The free body diagram shows the weight of the firefighter 6.30 meters from the bottom of the ladder, but we will now generalize this. We will call d the distance from the bottom of the ladder to the firefighter. If the ladder is not accelerating, the net force on the ladder must be 0. Two forces act in the x direction, G sub x and P. G sub x acts in the positive x direction and P acts in the negative x direction. Therefore, the sum of the forces in the x direction is G sub x minus P. Since the ladder is in equilibrium, this sum must be 0. Three forces act in the y direction. They are G sub y, W sub L, and W sub F. G sub y acts in the positive y direction, and W sub L and W sub F act in the negative y direction, so the sum of the forces in the y direction is gray minus WL minus WF. Since the latter is in equilibrium, this sum must also be 0. We can solve this equation for G sub y, and we find that G sub y equals W sub L plus W sub F. In example 4 in the text, the ladder weighs 355 newtons, and the firefighter weighs 875 newtons. So for that example, W sub L is 355 newtons, W sub F is 875 newtons, and the sum is 1,230 newtons. We have now calculated a value of 1,230 newtons for G sub y, which was the only unknown vertical force. We now know all of the vertical forces. We determined the value of G sub y using only the forces in the y direction. We used the fact that the sum of the forces in the y direction has to be 0 for equilibrium. We did not need to use torques in that calculation, and we did not need to use d, the distance from the bottom of the ladder to the firefighter. But we will not be able to determine G sub x and P without using torques and d. Before we calculate a value for G sub x, let's review what we know about that force. This will make our work easier, and it will help us understand our result. We know that G sub x and P are the only horizontal forces acting on the ladder. We also know that the ladder is in equilibrium. Therefore, G sub x and P must be equal in magnitude and opposite in direction. This means that if we calculate the magnitude of P, we will then know the magnitude of G sub x. We also know that static friction produces G sub x, and that G sub x is the force that prevents the ladder from slipping. When we have a value for the magnitude of Gx G sub x, we will need to check whether the static friction between the ground and the ladder can provide a force of that magnitude. If it cannot, the ladder will slide. Although we do not yet know the magnitude of G sub x, we do know that it equals the magnitude of P. This is as far as we can get using only forces. This is useful information because, using torques, we can calculate the magnitude of P more easily than we can calculate the magnitude of G sub x. For equilibrium, the sum of the externally applied torques must be 0. We will now use that fact to find the magnitude of P. G sub x and G sub y both act on the lower end of the ladder. Therefore, they both produce no torques about that point. If we use an axis through that point and perpendicular to the drawing shown, these two forces will not appear in the equation representing the balance of torque. The lower figure now shows P, W sub L, and W sub F. These three forces are the only forces we will have to consider when we calculate the torque about this axis. By choosing the axis at the lower end of the ladder, we have eliminated both G sub x and G sub y from the torque calculation. To determine the torques, we must first determine the lever arms for the three forces shown in the figure. Let's start with the lever arm for W sub L. W sub L is the weight of the ladder, and it acts at the ladder center, which is 4.00 meters from the bottom of the ladder, measured along the length of the ladder. W sub L is 4.00 meters from the bottom of the ladder, measured along the length of the ladder, but 4.00 meters is not the length of the lever arm. The lever arm is the distance between the line of action of WL and the axis of rotation, measured on a line that is perpendicular to both. We need to use trigonometry to calculate the length of this lever arm. In the right triangle that is now shown, the hypotenuse is 4.00 meters, and the lever arm is the side adjacent to the 50.0 degree angle. So, the length of the lever arm is 4.00 meters times the cosine of 50.0 degrees. Now, let's work on the lever arm for WF. W sub F, the weight of the firefighter. Remember that to generalize this example, we will use D for the distance from the bottom of the ladder to the firefighter, measured along the length of the ladder. W sub F is a distance D from the bottom of the ladder, measured along the length of the ladder, but D is not the length of the lever arm. The lever arm is the distance between the line of action of WF and the axis of rotation, measured on a line that is perpendicular to both. To calculate the length of this lever arm, we will again need to use trigonometry. In the right triangle that is now shown, the length of the hypotenuse is D, and the lever arm is the side adjacent to the 50.0 degree angle. So, the length of the lever arm is D times the cosine of 50.0 degree. We have just one more lever arm to calculate. That's the lever arm for P, the force exerted by the wall on the ladder. The calculation is similar to the ones we've already done, but as we will see, the trigonometry is a bit different. P is 8.00 meters from the bottom of the ladder, measured along the length of the ladder. But 8.00 meters is not the length of the lever arm. The lever arm is the distance between the line of action of P and the axis of rotation, measured on a line that is perpendicular to both. To calculate the length of this lever arm, we will again need to use trigonometry, but this time we will not use the cosine function. In the right triangle that is now shown, the length of the hypotenuse is 8.00 meters. And we now need to determine the angle between P and the ladder. The angle between the ladder and the ground is 50.0 degrees, and P is parallel to the ground, so, from geometry we know that the angle between P and the ladder must also be 50.0 degrees. The lever arm is the side opposite this angle, and the hypotenuse is 8.00 meters. So, the length of this lever arm is 8.00 meters times the sine of 50.0 degree. The lengths of the lever arms for W sub L and W sub F are proportional to the cosine of the angle between the ladder and ground, but the length of the lever arm for P is proportional to the sine of that angle. This means that if the angle between the ladder and the ground were to increase, the lever arms for W sub L and W sub F would decrease in length, but the length of the lever arm for P would increase. Now, let's summarize what we know. The table on the screen is the same as the table in the text with one exception. We have not used 6.30 meters for the distance from the bottom of the ladder to the firefighter. We have used the symbol D instead. This makes our result more general. Our result applies to any position of the firefighter, not just 6.30 meters from the bottom of the ladder. For equilibrium, the sum of the externally applied torques must be 0. We are now ready to use this fact to calculate the magnitude of P. Remember that P and G sub x are the only horizontal forces acting on the ladder, and, because the ladder is in equilibrium, they must add up to 0. So once we've calculated the magnitude of P, we'll also know the magnitude of G sub x. When we solve the torque equation for P, we get the expression that is shown. When we substitute the values for WLW sub L and WFW sub F, this becomes the equation shown now. And when we substitute the values for the lever arms, we get the equation shown now. Remember that P and G sub X are the only horizontal forces acting on the ladder, and, because the ladder is in equilibrium, they must add up to 0. Now that we have an equation for the magnitude of P, we can also determine the magnitude of G sub X. D is the distance from the bottom of the ladder to the firefighter. In the text, this value is 6.30 meters. If we replace D by 6.30 meters, we get that P is 727 newtons, which is the value given in the text. This means that when D is 6.30 meters, the magnitude of G sub X is also 727 newtons.